So today we're going to be revisiting projectiles and having a look at how we can make use of vector notation to solve and work with projectile problems. When we first came across projectiles in 2D, we were given the initial velocity as a magnitude and an angle of elevation. Well, now we're going to be making use of a vector form for that initial projection, and the two vector components, if needed, we could find an angle from them, but the angle is unnecessary. We can just work in this vector form. You'll notice that this way we don't really need to make use of any trigonometry, as we already have the horizontal and vertical component. But a lot of the calculations we're going to do are going to keep those two components together. And that will be true for all the SUVAT variables that can take vector form. So we're talking about the displacement, the velocities, both initial and current, or initial and final, and the acceleration. The only one of the SUVAT variables that cannot be a vector is time. Okay, let's have a look at an example. So here we're told that a ball is struck by a racket from a point A, which has a position vector 20j meters relative to the fixed origin O. This we can see in the diagram. Immediately after being struck, the ball has a velocity 5i plus 8j. So this is the initial velocity. This is going to be u when we collect our SUVAT variables. We're told to use I and j. After being struck, the ball travels freely under gravity until it strikes the ground at point B. Okay, so gravity, we already know, is going to be negative 9.8, particularly if we've chosen up as the positive direction. But in vector form, we need a horizontal and vertical component. The horizontal is 0. There is no acceleration horizontally due to gravity. And the vertical is the negative 9.8. This question has asked us to find the speed of the ball 1.5 seconds after being struck. Okay, let's collect some SUVAT variables and see where we go. So we don't know the displacement. We do know the initial velocity. That's going to be 5.8 in column vector form. Final velocity, this is what we're looking for. The acceleration, 0, negative 9.8. And the time, 1.5 seconds. From here, if we're looking for the final velocity, if we're looking for v, we need to use v equals u plus at. We're going to substitute in the vectors that we know, so that's the initial velocity and the acceleration. So we get this, and finding the resultant, we have 5 and negative 6.7. This is the velocity vector after 1.5 seconds. From here, we should be able to calculate the speed. It's going to be the magnitude of this velocity vector. To find its magnitude, we're going to apply Pythagoras to both of these components, the horizontal and the vertical. So we get 5 squared plus 6.7 squared. If we root that, we get 8.4 meters per second. So this was the speed of the ball after it had been traveling for 1.5 seconds. We didn't need to make use of trigonometry. We've done everything in vector form and found our answer with just a few lines of working out. In part B of the question, we're asked to find an expression for the position vector r of the ball relative to the origin at time t seconds. We know our position vector is going to be the original position plus our displacement. Well, we know the initial position, it was 20j, or written as a column vector, that's 0, 20. Now we just need to find an expression for s, for the displacement. Okay, let's go back to our SUVAT variables. The displacement is unknown, and that's what we're looking for. Once again, our initial velocity is 5.8. We don't know the final velocity, and our acceleration is 0, negative 9.8. And time is a variable. We're going to just call it t for now. Okay, so displacement is going to come from this SUVAT formula. We're going to substitute in our vectors. 5.8, t, 0, negative 4.9, t squared. Okay, so let's just resolve this right hand side. We'll get the resultant, and that actually is quite a nice vector. So this is the displacement from the original position. To find the position vector, we need the original position plus this displacement. So I'm just going to go back up here and add this on. So 0, 20 plus that displacement vector. And we can write that nicely. We get 20 plus 8t minus 4.9t squared and 5t for the I component. This is the position vector. This is exactly where the particle will be located at time t. This measurement is taken from the origin, not from the original projection point, but from the origin. For the final part of the question, we're asked to determine the distance OB. OB, we can see, is when the particle hits the ground. So we know its position vector is going to have a j component of 0. We don't know what the I component will be. We don't know that horizontal component, but the vertical component will be 0. Well, if I want the position vector's vertical component to equal 0, I'm going to set it equal to 0 and find the times when this happens. So 20 plus 8t minus 4.9t squared equals 0. Into your calculator, factorizing quadratic formula, however you get these two results, I get t equals negative 1.362 and t equals 2.9953. I'm not interested in any negative times. That will be before the point of projection. So 2.9953 is the answer I'm looking for. The distance OB is going to be that horizontal displacement. So what is the horizontal component when t equals 2.9953? What is the I component of the position vector? That's going to be 5 times t. Our position vector is 15, 0 when the particle is at point B. The distance OB is 15 meters. So here's how we'll approach projectile questions when we're working in vector form. There's no need to split into vertical and horizontal components. We can actually use them together in vector form. The purpose of vectors was to keep those two components together anyway, and we can make use of that.